So there are a few applications of magnetostatics I want to talk about. So from the last couple of boards, we've got this force that is exerted on charged particles moving at a velocity due to a B field. That's a mouthful. Most of the time, by the way, we will be dealing with B fields that are either perpendicular to or parallel to the velocity. So it'll be either sine theta equals 1 or sine theta equals 0. The first thing I want to talk about is the Hall effect. So there's a nice diagram in the book, but I'm going to reproduce something like it here. So imagine we have a current carrying wire. And in this wire, we have electrons that are moving to the right. And then we turn on a B field. So we have a B field that is going, say, stay with end of the page. So, by the way, the convention is if you need to draw a field that's going into the page, you use X's. And if you need to draw one that's going out of the page, you use O's. So we turn on this B field so that this wire is bathed in a magnetic field going into the page. So naturally, the electrons that are drifting through this wire are going to feel a force, right? So we use our right-hand rule. We point our fingers in the direction of the drift, just to the right, and then we put our palm in the direction of the B field, which is toward the screen. So our thumb is pointing up. And then we realize, oh, wait a minute, these are electrons, they have a negative charge, so the force is the opposite of what we expect. So it's actually going down. So the force on, so if we use the right-hand rule, that gives us the direction the force would act on a positive particle, and then negative will be the other direction. So what we'll get is we'll get a tendency for electrons to mostly move along the bottom of this conductor, right? And a conductor is just some piece of material where the electrons are free to move about a bit. So maybe this is a copper wire where the valence electrons in the copper are basically free to be wherever they want. And so if we have the electrons get shoved down to the bottom of this wire, that means that we're going to have a relative positive charge on the top of the wire.
Okay, explaining it. So which one's going in the opposite direction?
So
I don't know. Just explain all that again.
yeah.
I got
So
halfway.
we use the right hand rule to see which direction VB sine theta is going in.
Mm-hmm.
But then since we're dealing with electrons, Q is negative.
Yeah, okay. But so your fingers are pointing, instead of your fingers pointing to the right, they're pointing to the left?
No.
Or instead of your
Don't try to move your fingers in a different way. Just think
No,
that the right hand
the
rule.
force is going the opposite way. So then I have to turn my hand upside down.
No. So think about, because that you're going to sprain your wrist if you do that.
Yeah, but that would make it go down, right?
It would. So think of it as the right hand rule gives you the direction of VB sine theta, right? And then the presence of a negative sign just reverses that direction.
Okay.
Right? So yeah, it's it's tricky. Remember, negative signs in physics, all they do is indicate direction, right? So if you plug in, negative 1.6 times 10 to the minus 19 for the charge on an electron, that just gives us, that just flips the direction because of the negative sign. I know it is a little bit of a of a of a mind blow. Like, it's hard to it takes some practice to keep track of. But whatever you do, don't give yourself carpal tunnel trying to do this chapter.
I'm not quite that old. I can turn my hand over without hurting myself.
Okay. So we get this tendency for electrons to be on the bottom of the conductor, and the plus signs up there, that doesn't mean that protons are moving to the top of the conductor. It just means that the electrons that used to be at the top have now moved toward the bottom. So the protons haven't gone anywhere, but there's just an excess of electrons at the bottom and an absence of electrons at the top. And an absence of electrons gives you a net positive charge. So this separation of charge, positive on top, negative on bottom, it looks a lot like a capacitor or a dipole. Yep. Since we have, plates of it, so we'll have this separation of charge, which means we will have an electric field vertically inside the conductor. So there will be an E field from top to bottom. And the book uses L for the thickness of the wire. I think that's fine. We'll just use L. And wires are usually pretty small. So it's a fair approximation to say that because the wire is so thin, the electric field is basically uniform throughout the, just like in a parallel plate capacitor. So the voltage, the total voltage from top to bottom of this wire is just going to be the electric field that's induced times the thickness of the wire. All right. So far, so good? You'll continue to get more and more charge separation, which will produce a stronger and stronger electric field until you reach equilibrium, which is a little bit like terminal velocity from Gen Physics 1. So if we have this electron, right, because of the magnetic field, it wants to go down. Right? The magnetic field wants to push it down. But the separation of charges has created an electric field which makes it want to go up. So we'll continue to get a stronger electric field and more charge separation until these two balance each other out. And then that's the biggest separation that the magnetic field can provide. At which point we will have QE equals QVB. The Q's will cancel. And we will have E equals VB. What's the V in this case? What velocity are we worried about here? So if you read the chapter, and I know that all of you did because you are excellent students, this velocity, the velocity that electrons move through a wire with, is called the drift velocity. and it's typically pretty small. So in a conductor, the actual electrons might actually only move with a velocity of like couple of centimeters per second. However, um, electricity, like the wave of electricity that goes through the wire, travels at the speed of light. So you flip on the light switch, the light comes on instantly, like almost instantly. There's a speed of light delay, but almost instantly. But none of the actual electrons from the switch ever make it to the light bulb. They're just too slow. Okay, so we have E equals VB, where V is the drift velocity, and the drift velocity is related to the current. We aren't going to necessarily derive that right now. Just know that it exists. It's a thing. And we come back over here and say, well, this electric field, that's going to be the total voltage divided by the thickness of the wire. So we can actually replace that and say V over L. You know, where here I'm using the hat on the big V for voltage, using the little hats on it, and I will not use the hats on the little v for velocity. So the presence of a magnetic field can create a voltage from the top end of the wire to the bottom end of the wire. Right? So the presence of a magnetic field turns even a simple wire into a capacitor. All right. Questions, comments? Can we move on to the next thing? Okay. So the next thing, let's talk about. We know that the magnetic fields can produce forces on charged particles that are moving. So F equals QVB sine theta. This velocity, though, this is like delta x, delta t, right? That's what we mean by velocity. So what if we took this delta t? Well, it was like q delta x delta t b.
So is that still the drift velocity?
Yeah.
Okay.
So drift velocity is an inconvenient, like an inconvenient value to think in terms of, because current is what we normally measure, like the current in a circuit, and the drift velocity is related to the current, but you have to know like the internal resistance of the wire, what the wire is made out of, right? So it's inconvenient to convert that. So what if we take this delta t though, instead of letting it hang out under the delta x, we shove it under this q. Well, this charge per time, right? What is charge per time? What's another word for that? It's current. That's right. So if we have a bit of wire, and the current in the wire is headed, say, to the right, and the bit of wire that we're concerned with has a length of, say, L, that's going to play the role of our delta x here. So I, L, B, sine theta. So not only does the magnetic field produce a force on a single electron, it can produce a force on a whole wire that is carrying electrons. Right? So if you have a strong enough magnetic field, you can, cause a piece of wire to, so again, say if we have our B field going into the page, right, and our current going to the right, that's going to produce a force upward. Right? So if we're not careful, if we have a strong enough B field, we could cause this wire to tear or get damaged in some way. Hansen, that's a lowercase scripty l. L for length. Yep. So, side note, lowercase l looks a lot like number 1. So I always ended up, I ended up always writing my lowercase l's in cursive. I try and make my number 1s like so. You're always talking shade about my handwriting, Hanson. Okay.
Can look like
so magnetic fields can cause forces on current carrying wires, which potentially could damage those wires, which is a problem. Next chapter, we'll find that current carrying wires actually cause a magnetic field. So you put enough current in a wire, it can actually damage its neighboring wire due to the B field that it creates. Makes circuit design a little bit more complicated. For now, though, we're actually going to take this and we're going to talk about motors. So the force on a current carrying wire never getting into electrical engineering? Fair. You just be the best doctor you can be. Who remembers what torque is from Gen Phys 1? Torque. So, a quick review. If you've got, say, a door is a pretty good example. Here's the hinges on a door on the left. So the door is free to rotate around the hinges, and you come up and you push on this side of the door, right? Which is a certain distance from the point where it's free to rotate, and you cause a torque which is equal to the force you applied times the distance from the axis of rotation times the sine of the angle between them. Does that look familiar? Maybe?
Yes, it does, and it is still just as confusing.
Okay. This sine, by the way, comes from the cross product the same as Lorenz's law does. Because torque is technically defined as the cross product of force and radius. You don't need to use that, but that sign didn't come from nowhere, basically. So, this is torque from Gen Phys 1. What if we took a piece of wire and we bent it into a loop? Okay, and we set it up so that the way it was attached at the bottom is it's free to rotate around this axis, around its central axis here. So it's fixed in place other than it's allowed to rotate, you know, from say left to right or right to left. And say we run a current through this wire. So we have a current that goes through all the pieces of this wire. So far, so good. Okay. And we turn on a B field, which goes into the page. Okay. So the force on the bit of wire that the current is running through is going to be ILB sine theta, just like we got from the last slide. If we use the right-hand rule, on the top, fingers in the direction of the current, palm toward the screen. Oh, the force is up, right? So on the top part of this wire, the force will be up. The wire's not allowed to move in that direction, right? So that's going to produce no torque, right? Because the direction of the force and the direction of the axis, they're parallel, right? They're both going up and down. So no torque from that. On the bottom, because the current is going in the opposite direction, the force will be in the opposite direction. So actually, on the top and bottom of the top and bottom of this loop, the direction of the force cancels out. So there's no net vertical force from the magnetic field on this loop of wire. Let's look at the sides then. So on the side, fingers down, palm toward the screen, thumb goes to the right. So there's a force like so. And on the other side, did I draw this sideways? No, I think this works. No, I did draw this sideways. Pardon me. The field is supposed to be horizontal. So the B field should be going this way. Okay. Something wasn't quite right. So on the top, the direction of the current and the B field are parallel, so there is no force. On the bottom, same thing. On the right side, right? So fingers in the direction of the current, which is down, palm to the right, and then fingers will be pointed toward you. So the force is coming out of the page. Okay. Other side,
Why are the fingers pointed toward me?
your
Confused.
thumb is pointing toward you.
Ah, there we go.
Sorry.
Okay.
On the other side, fingers point up, palm points to the right, thumb goes away from you. So if we're pushing into the page on the left part of this loop rather, and we're pulling out of the page on the right part of the loop, that's going to make the loop spin around this axis that we've set it up for it to spin on. So now let's calculate how much torque that produces. So torque is equal to F R sine beta, but the force that we've got going on here is equal to I L B, and the force is perpendicular, right? Force is perpendicular to the direction to the axis of rotation. So beta is 90 degrees, so sine beta is 1. And then we have this r to deal with, where r is the distance from where the force is applied to the axis of rotation. So that this distance here is r. In your book, they do something convenient where they say the length of these side wires are L, the length of these top wires are W for width. And so we can write this R as a W over 2. Okay. So that's the torque on the left-hand part of this loop. We have another one of those on the right-hand part of the loop, though. Same amount of torque, same direction of rotation. So since there's two of them, one on each side, that gets rid of the half in the 2 in the denominators here. And then we have this factor of L and W, and if we've got a squarish loop here, L times W is just the area of the loop. And that torque caused by the magnetic field, that is how DC motors work. Right? You get a motor, you apply a magnetic field, and you probably create the magnetic field using a coil of wire. We'll deal with that next chapter. So you get this magnetic field going. It causes this loop of wire to spin, and then you take the torque, the rotational energy in that wire, and you use it to do something like turn the tires on your electric car. We have questions or comments? Why do we lose the L and W? Because length times width is the area. So that takes us up through chapter 22.8.
Okay, so going all the way back to the beginning,
Yes.
I really did get, I haven't been lost the whole time. I was only lost at the beginning, but then I basically figured out what was going on. But, okay, why does the B field only cause why does it only go in one direction? Perpendicular to, like, okay, I understand why it would cancel out forces going in the same direction and opposite direction, but why is it only going one direction perpendicular and not both? That's
On
I'm not
this
sure if I
slide or a previous
understand
slide?
all that. What's that?
On this
Oh,
slide
we're
or a
all the way
previous
back to
slide?
the beginning.
I'm sorry?
All the way back to the beginning of why it's going in the perpendicular direction.
You mean back
Yeah, probably here.
here?
Yeah. Mm-hmm.
You mean why does magnetic force only work perpendicularly?
Not so much why it only works perpendicularly, but why it only works perpendicularly one direction and not both, which I guess means why, yeah, because if it were both, it would cancel. So, yeah.
So yeah,
Yeah.
so you are right though that if you have, if you need the force to be perpendicular to both the field and the velocity, that actually leaves you two choices for direction. So like in this diagram here, your two choices that are for perpendicular force would be into the screen or out of the screen.
Right.
Right? And which one you get is determined by the charge on your particle.
Okay. All right. I mostly understand that.
The diagram that you, is it basically spinning?
Dolan, I can't hear you at all, man.
Sorry, on that last diagram you drew out. Do I understand it correctly that it's basically spinning?
Yeah, this whole thing is
Okay.
spinning.
Okay.
The left side of the loop is spinning into the page, and the right part of the side of the loop is spinning out of the page. Right? It's in the video that I showed or that I linked at the beginning of the class. There was one of the clips where Mehdi put a paperclip on top of a battery, and that paperclip kind of spun around the exterior of the battery. That's exactly what we're analyzing here.
That was actually kind of the image that I got in my head when I realized that it was spinning.
Sorry, I'm having a real hard time hearing you.
I was just saying that was the battery with the spinning paperclip. That's what I was envisioning when I realized this was spinning.
Yep, that's exactly what we have going on here. Today was only chapter 22. That's correct. And in fact, not even all of chapter 22. We got through 22.8. We will start next week with 22.9, 10. We'll probably skip 11. So 22.9 and 10 will be magnetic fields produced by currents. And then that will bring us right into induced voltages due to magnetic fields in chapter 23. In that case, the magnetic field is different around the axis, but the charges flow the same direction, so the effect is the same. Which case are we talking about, Anthony?
I was talking about with the battery on top of the magnet.
Oh, yeah, yeah, yeah. So um, that's right. So the battery or the magnet is a little bit more complicated, but it's the same idea as here. We put a current through a wire, and a magnetic field causes it to spin. All right. So if there are no other questions, I want to thank everyone for coming along on the journey today. This is the hardest part of 152. This part where we have to deal with E and M. 18 through 23. For us, we're taking like a month to cover that whole section. If you were an engineering student, you would spend an entire semester on that. So we are going really fast right now. And well, I will take that as a compliment, Nicholas. Thank you very much.